Terrible thing of presenting through Teams is that I can only see my slides and I can't see you. So that means you can probably make faces while I'm presenting, but also if you want to interrupt and if you want to ask a question in the middle, just don't hesitate to shout and try to stop me, because I will not see hand raised or anything like this. I'll start the presentation. So first to say that I tend to put a lot of examples and a lot of cases and projects in my presentation. So that's mostly what I'm going to do. And I always like to start with a nice picture to look at. This one is one of my son looking very thoughtful in Connemara. Generally, I try to find a story of why the picture is relevant to the presentation, but I have to admit I completely failed in this case, and I still don't know. So if anybody has any suggestion for why this picture works with that presentation, you're absolutely welcome to send it to me. Before I actually go through that, I just wanted to kind of make a small kind of summary of what Jean already just presented, just to show you a bit where I come from, and that gives a bit of context for the kind of work I'm going to describe today. As mentioned, I did my PhD in Nancy, in Loria, with Jean and Amedeo. And there I worked on semantic web technologies, on knowledge representation, and on reasoning, especially for cancer treatment and for reasoning over guidelines for cancer treatment. I then moved to Milton Keynes in England, in the Knowledge Media Institute of the Open University, where I worked much more closely with ontology engineering and semantic web technologies and linked data. I started as a postdoc in the NEON project, which was an FP6 project at the time, and work on a number of other projects, especially applying semantic web and linked data technologies to the fields of education and smart cities. I started as a postdoc, finished as a senior research fellow in a permanent position. And in 2017, I joined NUI Galway, which is a university in Galway, and became a year after that the director of the Data Science Institute, as well as a co-director of the National Insight Center for Data Analytics. I work there on a number of European projects, national projects, and industry projects. And I also included the logo of the CIKM conference I organized last year, because that took a lot of my time. As you can imagine, starting the organization of a large international conference before the pandemic and before lockdown, and having to move to an online conference was a bit of a funny challenge. But I'm not going to talk about that today. As I mentioned, I tend to do presentations like this by showing a lot of examples that relate to a general concept. And to introduce the concept, I actually found a good introduction to it in the book Conceptual Structures from John Sowa. I started rereading it recently simply because it was there sitting on my desk. I have to admit, I actually didn't go much further than page 12. The one thing that I found interesting in that book, and he doesn't mention it very often, it's only in 2 places in the book, is the explanation of the distinction between analytic statements and synthetic statements. So he explained that analytical statements or analytic statements are statements which refer to general axioms, are statements that are universally true. They are the expression of something that is true and will remain true, such as all humans are mortals. And he makes an opposition to with synthetic statements, which are statements that come from observation. For example, every day Bob wakes up at 6 a.m. This might be universally true, but we can't guarantee it. It's something we know because it has happened every day that we can observe. But it's possible that Bob will wake up tomorrow at 7 a.m. and that statement will no longer be true. Now, the reason why I find this interesting because I think it, besides being a good explanation for the difference between being driven by intention, which is by definition, and being driven by extension, which is by observation, it also, in my view, encapsulates the difference or the gap between knowledge-based systems and systems based on ontologies, where those analytic statements are, and where, say, knowledge is encoded and represented to be universally true, and the very popular trends currently in artificial intelligence around machine learning and data mining, which aim at extracting synthetic statements, observations in the data, which we hope are universally true, but are really based purely on observation. And say that gave me, say, in a more abstract way, it's looking at, say, on the one side, systems which are knowledge-driven, which are really the kind of things we were mostly doing around the semantic web area and in knowledge representation and in reasoning, compared to approaches which are data-driven in artificial intelligence. And what I think is a very important field currently, and something that connects a lot of the projects I've been involved with, are those two areas, those two kind of approaches and those two kinds of statements relate to each other. Our analytical statements are grounded by synthetic statements, and our synthetic statements can be interpreted by analytical statements and explained by analytical statements. So how you connect data to knowledge, and through doing that, connect different approaches to artificial intelligence. So a lot of the examples I'm going to quickly show you today relate to the two challenges associated with making those connections between knowledge and data. And one of the key challenges is obviously to get access to the data. And by access, I mean something which is more precise than just being able to get to it. And it means something which it means having access in a way which is processable, that machines can look at, that machines can represent and reason upon, so that they can be processed and reconnected. And then so that we can link the data-related processes with the knowledge-related processes. I've focused first a bit on this notion of access to data and knowledge, because this is really what is at the core of the idea of the semantic web and linked data. So I'm not here to give you a lecture on what the semantic web is. I'm pretty sure you wouldn't want that. But my very short summary of what it means, and especially what linked data means, is the idea of using the architecture of the web to publish and represent data and knowledge. On the one hand, the web represents is a universal network across machines and across locations of documents which are connected by hyperlinks. The idea of linked data is to represent data by a network of entities, data objects, which are connected through something which is similar to hyperlinks, but that represents semantic connections between those entities, knowing that each entity, each part, or each object of the data might be sitting on a different machine in a different server at a different location, but that this overall set of connections between entities form one universal network of data objects, which is the linked data cloud. Now, a few years ago, we really had to explain that this was a great vision and that a lot of work was being made to actually implement this great vision through technologies such as RDF, OWL, and Sparkle. The reality is we don't really have to do that anymore because a lot of it has happened. This is an image of the linked open data cloud, which is a registry of data sets which have been published through linked data principle using those web technologies, and of the links that exist between those data sets. So that's hundreds of data sets available on the web through web technologies, directly accessible, and that connect with each other in a way that makes all of the data in all of those data sets accessible and addressable as if they were one shared network sitting in the same place. One part which is very interesting in this network is that it also represents, in a more abstract layer, a network of ontologies, a network of concept and representations. So the ontologies are the schemas, the semantic schemas that represent and that are used to structure those data sets, but also that includes the semantic statements that represent the knowledge of the domain that enables the interpretation of the data and interoperability between data sets that can be connected through ontologies. One of the great things of the semantic web is that the ontologies themselves are represented with the same principles that are used to represent the data, which means the ontologies are connected, the ontologies are addressable through the web. And this means that in addition to a layer of information, the semantic web creates a layer of semantic statements, a layer of ontologies, and of ontological concepts that can also be addressed. So that is a very kind of, say, short introduction to the semantic web and to explain, the main concept. But what it means in practice is that it enables creating data platforms that are accessible and available through the web. So my favorite example of this is a platform called data.open.ac.uk. It's a system I started developing with my team when I was at the Open University, and literally on the basis that we were arguing that semantic web technologies and linked data technologies were very helpful in enabling to surface data and information and knowledge that exist in a heterogeneous system in a way which is easily addressable. And that at the same time, we were in the largest university in the UK. At the time, the Open University had 200,000 students per year. And if you don't know the Open University, it has a particularity to be a distance university. So there is no student on campus, which is very relaxing, by the way. And all of the teaching is done online or through a few face-to-face tutorials. Which means that it's very important for this organization to make sure that information is well surfaced and well available, and that all the different parts of the university can talk to each other at the level of information systems. So what we did with Data OpenSC UK is exactly that: extract data from a lot of different systems to represent it as linked data so that it can be visible and processable on the web by any part of the university, but also connect to the rest of the world and be represented according to ontological statements that really semantically captured what they mean. So this is an example of the representation of the organization itself, the Open University, and how this representation can connect to the linked database representation the UK government had of the university, with addition, and therefore bringing more information into it, and how we can state within that knowledge graph of the university that the university offers, for example, the course called M366, which title is Natural and Artificial Intelligence, which I didn't choose randomly because that was the one I was teaching at the time. And that this course has a number of components. It connects to information about the books that are relevant to the course. It connects to the resources. It connects even to the system to register for the course, how much you can pay, or as shown here, from what location, since the university is a distance university, so from what locations you can take the course and you can register and be a student for the course. So that's, again, that sounds like a relatively simple thing to do. It's representing the information of a very large organization into a graph which just happened to be represented on the web, and that follows a schema which is understandable through the web. But what that leads to is, first, that it makes a lot of things much easier in terms of application development. This is a subset of the kind of applications which were developed using data.open.ac.uk, which include applications that can relate, for example, what you're watching on TV to a course at the university. So you can go to the BBC iPlayer, which is the online streaming application of the BBC, and click on a little button in the application we have developed to get a list of educational resources, material, and courses that the European University offers and that you can look at if you are really interested in the topic of that particular TV show. We did a lot of stuff around open educational resources and around kind of connecting all the content that the university provides in different ways so that students, and especially potential students, can enter in one place and follow all the trail that connects the different resources at the university. We also did a number of things to connect people, and one of the really interesting parts of building this system, we realized afterwards, is also around connecting research. We could, as a result of what we did, connect teaching to research, connect researchers with researchers, understand how networks form out of publications in research groups, and that was especially useful when we had to report at university level on the research performance of the institution. But one step much further than that is, say, I'm actually quite glad to say that first, data.open.ac.uk was the first ever linked data platform of a university. Nobody else had done it before. And you can go and look it up. It still exists. It's still running. The university is still using it as a core system. And one of my colleagues was actually hired, and as his job is to maintain that particular system that came from research and was implemented within the university. But the other thing is that even though we were the first, a lot of other universities followed up, especially Oxford, Southampton, some universities in Bulgaria, universities in Spain also started to express their data, express information about what they were doing, about the courses they were offering, about the research they were doing, through linked data and publishing that through the web. And again, one of the beauty of the semantic web and of linked data is that because we all do that through web technologies and using similar ontologies, we can all reconnect this. So this the graph on the left represents all the data sets we could find that were were published by universities about their activities, and they are connected by how many concepts they share. So a data set will have a connection if it refers to the same concept as the other. And we can really look at the graph of connections at data set level and understand all the different areas universities tend to look at, and the colors here represent partitions after applying a pretty standard network partitioning method, so that we can look at all the data set and see that some of the data sets, for example, the red ones, are the ones that tend to look at resources, course material, and things like this, while the blue one represents things like buildings and organizations and departments, while the green one represents research. And we have an overview of what the educational sector tends to do through the data that is represented in linked data. The graph on the right actually encapsulates that by extracting those concepts that are mentioned in ontologies in educational data sets and connecting them through their co-occurrence. What that does effectively is make emerge from a lot of different data sets what is the ontology of education, what are the concepts that educational institutions tend to work with, and what are the concepts which are very important to the organization of education and of teaching. And that is all done again through looking at data from across multiple organizations which are all connected with each other, and that allows us then to compare and contrast and connect what one university will do compared to the other. Now, that went, by doing this work, we realized that there is currently a lot that can be done in providing more information to in education, especially to learners, and making it easier by using this kind of information for learners to get to the right resources and to themselves understand their own learning. And that led to the creation of the AFEL project. So AFEL stands for Analytics for Everyday Learning. It's a European project that finished in 2018 and that I was coordinating. And the idea of AFEL is starting from that part where we looked at very carefully of information available to universities or from universities, look at how we could connect this to information that exists outside of the university, information that students and learners generally would use in addition to what the university provide, and to try to get an overview or a complete view of what it means to learn for a learner, and to provide them with this information so that they can understand and analyze their own learning through their own activity. We were involved a lot in an area called learning analytics, which really is about trying to analyze or use data science, data analytics, and artificial intelligence methods to understand how people learn and how people organize their learning. That led to a series of applications that enable learners to look at their own behavior with respect to learning, starting from extracting automatically the kind of topics they were of the resources they were looking at, which ones they were focusing on, and doing some additional semantic analysis of those resources to understand their complexity, their diversity, and their coverage, so that we can give a picture to the learner of what it is that they are learning and how they tend to be learning, what is their general learning behavior, in a way to provide them with the base information for them to set up their own learning goals and organize and direct their own learning. So that's kind of, you know, the where we got with the education area, through this idea of having data and knowledge accessible and available that can be processed through the web and at web scale. Now, obviously, education is not the only place where that is useful to do. And another project in which we applied that quite extensively is the one of the called MK Smart. So MK Smart is quite a big project, which basically goal was really to make the city of Milton Keynes, where the Open University is, a smart city. And to do that through creating a data infrastructure, through creating a data hub that will include a very large variety of data about the city and around the city and about people living in the city, in a way which is semantically described and semantically organized, and again available through web technologies, so that citizens and businesses in the city could use this information to improve a number of aspects of the city. I say citizens and businesses as well as the city council, obviously. So we applied basically the same method, and I was in charge of the creation of the data, which again is a system that is currently still being used by the city to organize our data sets can go into such an infrastructure, can be integrated, can be organized, and can be made available so that they are exploitable, but to create applications that make use of the fact that this data is available as one shared graph, as well as of the fact that it's represented and semantically available for processing. That led again to quite a large number of applications, in particular connecting sensors or satellite imagery to with information about the city generally, as well as the applications for people to be able to connect their own sensors and get predictions and get classifications by introducing data from the city as context, to even games card game, or say online card games automatically generated out of data from the city. And one of my favorite and something I'm very happy about and very proud of, we even managed to connect the MK Data Hub to Scratch so that kids could program their own dashboard using data from the city in Scratch and actually get to be introduced to coding with information directly relevant to where they are living. So that's a very important project for me because it again encapsulates how by say making data available, having data as a commodity that is directly exploitable through a data platform that is enabled by knowledge technologies. We can enable a lot of other things to happen, and a lot of the heavy lifting of using those informations is much easier to deal with. One of the aspects of that particular system that relates it to ontologies and to knowledge structures in particular is also that we wanted to make sure that the data coming in was properly represented itself, so that at the level of the metadata, at the level of the description of the data sets themselves, we add a semantic representation so that the connection between data sets and the connection between the data sets and especially their terms of use was properly represented. So that's a work especially with one of my PhD students who was looking at data cataloging of how to represent through ontologies the terms of use or the terms of conditions or the rights associated with the reproduction, distribution, and application of data, but also to represent through an ontology and knowledge graphs the workflows and the processes that were applied to data to get to the data, so that the connection between data sets can be represented by a relationship that describe what was done to get from one data set to the other, and so that we could reason upon what was done to data, where it came from, what was the provenance, but also we could reason upon the rights associated to data and have a clear understanding of how those data processing workflows affected the right to distribute, reproduce, apply the data in output. And that's an example which is a bit different from others of how, say, the knowledge-based approach and the use of ontologies and the use of semantic statements can help in interpreting and in working with data. It's in data-driven approaches. Now, there is one system I have to mention, even though it's a bit different, it's because I keep talking about ontologies in the context of large data repositories and the context of representing data on the web. Now, one of the first things I found when I joined the Knowledge Media Institute in England is that a tricky part of this, a really difficult part to do this, is to actually find the ontologies and find ontologies that we know will work with the system we have in place, we know will connect to the data that we are trying to represent, and make sure so that we can find the definitions of concept and those semantic statements that we can apply to the data in order to make it work. So as a result of a realization that none of this existed really, we started in the team developing the Watson Semantic Web Search Engine, which is really literally a search engine for ontologies, where we can search for concepts that are represented in any ontology that will appear on the web. Unfortunately, after about 12 years of existence, that system was shut down last year, mostly because I had left the Open University and there was nobody left to take care of it. But in the meantime, we did manage to develop quite a number of very interesting applications that, in that case, really, in contrast to the other applications I have mentioned before, were looking at the knowledge layer of the semantic web, and we're really looking at the connections between concepts. So that, the one on the top here is a small demo of using this as part of a semantic web search engine, where we can use the information from thousands of ontologies on the web to say specialize or generalize queries, and to kind of refine queries to actual normal web search engines. But we also integrated this idea into the environments to create ontologies and to engineer ontologies through being able to find concepts, so that someone can create an entirely new ontology by picking concepts that exist from in many ontologies from across the web, and check then afterwards whether the statements they made were agreed by other ontologies, or in the contrary disagreed. So this is one that I was particularly proud of, which is a plugin for an ontology editor, where the ontology currently being created could be assessed based on whether or not other ontologies agreed with the statements it made. So you can see that this one in particular was very much agreed upon by almost everybody on almost all accounts, except for these statements here, which, if I remember well, said that an employee is a person. And that is actually a statement which ontologically is incorrect, because it is an employee, being an employee is a role that a person take, and being an employee is not a subset of a person. And that could be detected by looking at other ontologies on the web and understanding that they disagreed with that statement and that it should not be there. That other example is an interesting one also, of connecting concepts through passes within ontologies, and so helping with the ontology matching task, which is a task of trying to understand how concepts in one ontology relate to concepts in other ontologies. So that, say, again, is a very quick run through of some examples of how this idea of making data and knowledge available and processable on the web, making data and knowledge accessible, can help a lot in a lot of situations. And many of those examples already connect the two aspects by grounding the knowledge in data, or by using knowledge to represent data, by connecting ontologies with the data being represented, and by doing so enabling a more meaningful use and manipulation of those data. But one thing I really want to focus on in the last part of this presentation is how the availability of knowledge represented through knowledge representation and through semantic web languages, and especially through large knowledge graphs, can help interpret data, and especially interpret the results of data processes, in particular machine learning and data mining. So this is really about how do you use knowledge for explainable AI. One of the first work we started doing in my team is through the PhD of Ilaria Tidi, who did a PhD on explanation, and a starting point was to try to understand the meaning of explanation. So how do you define what is an explanation, and in different disciplines? So she reviewed the notion of explanation in many different disciplines, including medicine and cognitive science and psychology, to come up with an ontology representation of what an explanation should be. It's not a very complex work, but I think it's a very important work, because it gives a semantic foundation to the idea of explainable AI, and to the idea of, verifying that explanations we come up with are semantically valid. And basically what it says is that an explanation is something which has an event to be explained, an event that explained it, but importantly that those two events have to share a situation. They have to be within the same context, and that the explanation has to be based on a theory. There has to be a more abstract version, say, definition of the explanation that can connect those two events other than a pure coincidence. The work of Ilaria was really about trying to find explanations for data phenomena, and especially for things we can find if we do a bit of data mining. So the examples here of this work include trying to understand or explain why some countries, say, when we look at the gender distribution of education in countries, some countries have more say, males being more educated, and some others are females being more educated, and some others are more equal. What is the explanation for this? Another example is trying to explain how research networks form. So how is it that if we try to cluster using a network partitioning method a number of different researchers, what we find is that they will tend to form around groups, and how these groups tend to appear. And one of my favorite one is explaining peaks and significant events in Google Trends. So Google Trend, in case you don't know, is a service of Google that tells you how many times a particular query has been sent to Google at a given time, and trying to explain why those trends appear and what happens. So using the example of the countries, the way Ilaria went on to do that was by using knowledge graph and using all the data and knowledge available on the web, or the kind of knowledge-based representation of the data available on the web, to find connections between the thing to explain, the group of countries, for example, where males were significantly more educated, with characteristics of those countries by basically following a path in that very large knowledge graph that is the linked data cloud. What is really important and interesting with this work is that it encapsulates the idea of using knowledge from the web. We don't put any knowledge into the system. It's the web is the knowledge base to come up with explanation and explain the result of a local data mining method that has used its own data. Some of the example we got on that particular use case is, say, countries where men are more educated than women tend to be countries that are less developed and have a high PPP, which I'm not sure what it means. So again, this does not sound like a very complicated and very surprising results. But what is really fascinating about this is that it could find that without us telling anything about it. We didn't tell the system that the problem was about countries. We didn't tell it to focus on a particular data set or to look at one particular case. It just went on to search on the web the information that could potentially connect the phenomenon and the clusters we had found with characteristics of the elements of those clusters. My favorite example of all is the one on Google Trend, and one that Ilaria was using a lot, which is to try to explain why there were certain times where people were looking a lot or querying Google a lot with the query "A Song of Ice and Fire." The reason I like this example is that somebody who knows the domain, somebody who has knowledge of what a song of ice and fire is, will know the explanation. It's easy for somebody to figure out this is why those peaks happen, or at least to have an idea about it and verify it. Somebody who doesn't know anything will not have any clue at all. And again, the great thing about this particular system is that at the same time, it doesn't know anything because we didn't give it any knowledge, but it also knows everything. because it has access to all the data that exist in the linked data cloud and can follow this data and can represent this data in a way which is semantically valid and semantically interesting. So as you can see, some of the explanations are not particularly valid. Like, it's a pure coincidence that those peaks happened at the same time as there was event in the Ukrainian First League. But it did find that a possible explanation is that those peaks happened when a new episode of the TV series Game of Thrones were being released. And and that is the explanation, I believe. Anybody knowing the domain, knowing A Song of Ice and Fire, will probably come up with as well. Now, as I was saying earlier, one important thing of a valid explanation is that it has to happen in the same context and it has to have a theory. So one follow-up for this particular work is, now that we have candidate explanations, we can try to reconnect the elements of the explanation with the origin of the data, with the entity A Song of Ice and Fire, so that we can see that in principle there is a connection with between Game of Thrones and A Song of Ice and Fire, and that connection is much stronger than the connection that exists between the Ukrainian First League and A Song of Ice and Fire, which we can find a connection between the two, but it's very weak. So that led to in particular a work in identifying strong connections in large knowledge graphs on the web, and using this to filter potential explanations for those data phenomenon in a way that turned out to be quite efficient. The last work I want to mention is a more recent one, and it's one about model interpretability. So the idea of explainable AI in many cases is about trying to explain specific results. So the use case, which is a work we did with Andrei Nikolov last year, and it was published in October, is we wanted to look at model interpretability, and we looked at one specific use case, which was which made it easy to look at that particular problem, which was to use a machine learning method to predict, given the biography of a painter, whether or not this painter would be will have his painting exhibited in a major European museum. So that's an example of the biography. And in this particular case, if we train a model to predict that, the model will say that this particular painter is unlikely to be on display in a major European museum. Now, the principle of explainable AI is that we want to be able to ask why that is the case. And the current explainable AI methods, most of them, will focus on giving a surface explanation to this, which is what are the parts of the data input that have influenced the classification in one way or another. So you can see that the name of the painter in that case was quite a positive thing. But the fact that he was Italian and that several places in Italy were mentioned in the biography was a negative influence, while being related to Western art was a positive influence. And in the end, it looks like the explanation for that particular case is this person is unlikely to be in European art museum because somehow they are linked to Italy. And that is not a particularly satisfactory explanation, both because we still don't understand why that is, and because it doesn't explain the general behavior of the model. It just says that particular case is like this, and maybe somebody else from Italy will be classified differently, and somebody from another place might be classified again differently. So what we did to get to model interpretability is to reconnect the input to those models again, to the large knowledge graph, which is a linked open data cloud available on the web. And then we took this input and we took the output, and by connecting it through the knowledge graph, we could extract characteristics, similarly to the work with Ilaria, the characteristics of entities which tended to push towards a positive outcome, and characteristics of entities which tended to push towards a negative outcome. And by a simple and standard process of rule mining, we could extract rules that connected the characteristics with a classification. For example, that if a painter had, say, if the biography of a painter mentioned an entity which was a commune in Italy, and especially located in the province of Perugia, then the model will tend to classify that particular example as negative, so not likely to be exposed in European museums. So we had very interesting results coming out of it. I mean, the individual results are actually quite fascinating. So, for example, we can now say that this particular model, based on the data it was trained to use, will tend to think that painters from southern Netherlands are more likely to be exposed in European museum, or this is a rule that the model is using. Similarly, painters that mention work that represent the Virgin Mary are very likely to be classified positively. On the other hand, as I mentioned before, painters mentioning certain places in Italy are likely to be classified negatively. So the really nice thing about this is that it gives a set of rules that explains the behavior of the model as a whole. It says, this is what the model does. And we can look at these rules very generally. On the left, these are the entities and what characteristics they are and what connections they are that tend to push the model towards a negative classification. So Dutch artists, Flemish artists, things that relate to Christianity and especially Christian paintings, and Spanish artists. On the right, the entities and their connections that tend to lead to negative classification. For example, the fact that the artist is Korean, Russian, Greek, or Chinese. Again, those are not particularly surprising things. But what I think is really good with that approach is that it allows us to debug the model. It allows us to look at whether those rules actually make sense, if they are validated by domain knowledge of the domain. For example, we thought that it was very strange that painters from Italy tended to be classified negatively. And it is really saying that the model used information that Italy is a location connected to the painter to make that particular classification. By looking at the data, we realize that a lot of the painters in Italy, or Italian painters in that particular data set, focused on frescoes rather than paintings. So basically they painted on walls, and that's very hard to put in a museum. So the data says that Italian painters tend not to be in museum, but not because they are Italian, because of the kind of work they have done. And probably we should unbias the data and retrain the model so that it will stop using the information about the location being in Italy as an indicator, because this is not the reason for making for that rule is basically incorrect. Now, interestingly, on the other way around is that sometimes we can find rules we didn't know about, and we can extract rules that tell us a bit more about the domain if we can validate them and if we can show. So that's really that connection between the synthetic statement, which is here is a rule that the data seems to apply to the data, towards the analytical statement, which is that is actually a piece of knowledge about the domain which is valid and understood. And a last bit, which is sorry.
Ouais, c'est. Bah, comme je t'ai dit, j'ai parlé avec lui quelques fois. Bah, il est vraiment.
Okay. I don't know if you hear that, but I hear it too. So I'm just going to finish very quickly because I might see that as an interruption. So yeah, so the last bit about that particular work, which I found personally very interesting, is that it is a way to test the generalizability of models. Say machine learning models currently are, I think, have a serious issue that it is very difficult to assess whether they can be applied on another data set than the one on which they were trained and tested. And the way that particular work can be used to do that is that the rules that are extracted, we can look at them and see whether or not they include elements of the domain, or they use things which are outside of the domain to make an assessment. And to test that, we had a lot of argument with Andre about this. We tried to run the same model using, instead of using the biographies of painters, we use the biographies of footballers. And Andre was very upset, but we knew in advance that what he would do is that it would actually say that some footballers were likely to have their work displayed in major European museums, because we know that the rules do not use information, or not all of them use information which are actually related to the area of art and paintings. And therefore that this particular model cannot be applied beyond that particular domain. So sorry, I took a bit of time. I'm going to conclude very quickly. And I say this kind of might feel a bit like a list of examples. But what I think all those examples have in common is that what they do in the end is look at the idea of intelligent data understanding. The thing that connects synthetic statements and analytical statements is the notion of understanding what the data says in terms of the knowledge we have, and creating new knowledge from the statements we have, from the data we can analyze. And that can be decomposed into three ways: understanding the provenance and access to the data, and we can see that through the examples I gave in education and smart city. Understanding where the data come from and how to get to it is a very good first starting point. Understanding the content of the data and really bringing the data to a semantic level so that we know how to process it. And finally, understanding the results of analyzing the data, as in the last two projects I just mentioned. Sorry, I took a tiny bit more time than expected. This is not even a complete list of all the people I need to thank for having contributed and collaborated with me on all these works. And I hope you enjoyed it.
Thank you, Mathieu. Thank you very much. I applaud, but I think other people also do it. Well, I think we have some time for some questions. Oh yes, there's a way to do it via Teams. I do it also. Okay. So anyone has a question for Mathieu? I have some, but I think I have other questions. Raise your hand if you have a question. Okay, but I have questions. Which one? On one, something you have said about this is just a detail of your very complete talk about Scratch. What it's intriguing to have students, children, in fact, making some programming using Scratch. And I was wondering, could you give us an example of what a young programmer could do with Scratch? Yes.
Yeah, no, sure.
An example of application, yeah.
Yeah, no, I mean, it's Scratch generally is used a lot for animation and games, and that's really a way to get kids into it. I actually did. I created a course for young children in NUI Galway. There is an association called Youth Academy that gives courses, summer camps to kids between 8 and 12 on game development for Scratch, using Scratch. And it's an interesting concept. That particular, say, element of the talk was about, say, using connecting the data from the city into Scratch. So most of, again, it's kind of similar in a sense, which is the kind of applications that could be developed with that, and that, you know, the kind of things that kids will do with this is again, mostly animations and games. So there are a few examples around, you know, making animations showing the rise in temperature and, you know, how the temperature and soil moisture, for example, will relate based on using streams of data from temperature sensor and moisture sensor, or games like the one on the left, which was on the right, sorry, which was not developed with Scratch, but similar games can be developed with Scratch around, you know, using information, for example, about the estate, the different areas of the city, to make a game where, like a board game, where they will compete with each other based on their characteristics like population, health, and, you know, other stuff like this. So it's a really interesting concept, I think, and I was not in charge of it, but we had, as part of the MK Smart project, a very strong education element, where the whole idea was getting kids through applications like Scratch to understand data analysis and what they can do with data, and how the availability of data can enable them to understand their own city better.
Okay. Well, thank you for this answer. Any questions from the audience? This is the beginning of afternoon. Everybody has lunch. Some I think I have. No. Nobody raises hands. Okay, I have some questions. I think it is important for a lot of people about the explanations. We have this discussion some time ago about several teams are interested by this notion of explanation, explainable AI. And here, what I understood is that Ilaria, your PhD student, has developed an explanation pattern, and that the way you use it is in a given to give an explanation to a model learned from some machine learning technique or something else, is to match this explanation pattern with linked data. That's it for the moment?
Yeah.
Okay.
Yeah.
So this match is, you search only for exact match, or sometimes you need approximate matching?
No, that's a good question.
Well, thank you very much.
Yeah, because the previous one was not, obviously.
Yes,
no, it's not what I meant, obviously, as you know. So, I mean, in short, it's an exact match, as it was, but say it's an exact match which also takes into account notions of confidence. So the way the data in linked data and they say the knowledge graph is matched against the pattern and is matched against the entity and the result of the model is exact, but say how much it matches the set of entities that need to be taken into account is approximate. So it's based on confidence. Okay. I'm not sure that really answers, but
yes,
in short,
well, it's a way to do some approximate matching.
Yeah,
actually, but the structure is exactly matched, but with some confidence levels. Okay. So my next question about explanation falls. It was what when there is a complete mismatch of the explanation pattern, does it occur? And the answer is no, obviously. So any, I think someone has, I see, Nicolas J.
Hi, Mathieu.
Yes.
Nice to see you again.
Hi, Nicolas.
And thank you for your talk. My question is in the domain of explainable AI also. You show some example of explanations working with association rules mining or frequent item set mining. And do you think that the linked data approach will work with many other kinds of machine learning methods, or such as neural networks? Or
no, that's also a good question. Thank you. Well, first I have to say the first work with Ilaria was mostly based on clustering methods and as well as association rule mining. The second work from Andrei is based on explaining neural networks, but by using an association rule mining method. So yeah, I do think it will work, but considering that, say, in some way we don't really look into the neural network model, we work around it by trying to rematch knowledge we have from linked data and from ontologies into the results of the machine learning model. So we obviously use the things like lift and deep explainer to get the initial kind of surface explanation of which features of the neural network is mostly used to get to a decision. But then having extracted that is where the linked data method and the association rule mining method is being used. It's an interesting, say, area to try to get actually deeper into the neural network model and to integrate those kind of knowledge directly into the model. And especially in the last work, this is something that, say, when I was mentioning debugging the model, currently the way to do that will be to fix the data and retrain it and retrain the model. But it will be really interesting to actually realign properly those rules with the topology of the network so that we can actually manipulate the network directly to deactivate rules that we believe to be invalid. Not sure that answers the question, but
yes, thank you.
So, other questions? I have one. I have other ones, but I think I will ask only one. It's about speak about agreement, especially, and maybe there's some disagreement somewhere in part of your talk. You hear me, Mathieu?
Yeah, I do.
Do you see what it was when you speak about agreement and disagreement?
Yep, this one.
Yeah, I think so. Okay. I have not heard the word merging, but when I hear disagreement, agreement, there's some merging idea not far away. Would you agree on this?
Merging.
Merging, yes. Do you merge data or knowledge in your, or is it not the purpose of this agreement and disagreement statement assessment?
No,
No.
Well, no. Basically, the purpose here is purely assessment. So we don't merge the data or the knowledge from the agreeing or disagreeing ontologies. At this stage, we purely assess whether or not the other ontologies tend to agree or disagree with the statements being made in the one currently being edited.
Well, which is a way to do some, I would say, merging. Even if you don't have the merge ontologies, you make some inference on the. You have the various ontologies, and you make some dynamic merging and make some inference from it. No? You can see it this way.
Yeah, no, kind of. Say the method doesn't involve merging, but say in principle you could see it as a way to reason on a merge ontology, or say on sub say merge sub ontologies. So basically, mostly it's about looking at whether this statement in the context of the statements of the other ontologies will lead to an inconsistency. That's relatively straightforward.
Oh. See, if you have inconsistency, this means that you have you don't work at RDFS level. You work at OLDL, something like that.
This is mostly looking at all, but also, I mean, I'm making a quick answer, but in reality, we base the notion of agreement and disagreement on a relaxed version of inconsistency, which is not only the pure logical inconsistency, but say an informal, say, or a less formal version that statements saying different things, even though they might not be logically inconsistent, will be considered to be at a certain level of disagreement.
Can you give an example? But I don't get it.
So, well, a simple example is if one ontology says that that person is a subclass of animal, and the other ontology says animal is a subclass of person, they are not inconsistent with each other. But in our framework, we will consider them to be disagreeing.
This could be managed via a closed word assumption. If you make some, here you have some inconsistency that you can get in your simple taxonomies, just making, here you say that human and animals are not, person and animal are equivalent, which, but it's inconsistent if you consider something like a unique name assumption. That's right? That's what you meant?
Yeah, not really. Not really, because in any case, if we introduce a unique name assumption, then we can't do anything because the first step is to actually match them and make them equivalent. So it's basically based on a set of rules that assess how different types of axioms would lead to different levels of agreement and disagreement. So, for example, the rule that say if one ontology says that something is of type another thing, and another ontology says that that thing is a subclass of the other thing, they disagree a little. Now, if one ontology says that thing A is equivalent to thing B, and the other ontology says that thing A is different from thing B, then they disagree a lot.
Yeah. Yes. Well, disagreement in the first example is that non-respect of some pattern of ontological pattern. You should not have both X type A and X subclass of A.
No, that's actually no, that's a very correct way of describing it. Disagreement is logical inconsistency or say undesirable patterns in the merged ontology. We just don't merge it, but it's if we merge the ontology, it will lead to undesirable patterns.
Okay.
One of the very interesting things of this particular work, I mean, it's one of my favorites, is that we also used it to try to find consensus or controversies. So basically, given a statement, we could say whether ontologies on the web generally agreed with it. So if there was a consensus that this was correct, or generally disagreed with it, which means there was consensus that it was incorrect. or if there was no consensus, so that different ontologies had different views on that particular statement, and the controversial statements tend to be the most interesting ones.
Okay, well, this is very interesting. We should discuss about it sometime.
Yeah.
Do we have are there other questions?
May I?
Yeah.
Yeah. Hello, thank you. So yeah, my question is about this plugin. So is it operating only on the T box or also on the A box, on the schema level, or?
It's a very relevant question. So it operates on both. That's the short answer. So it can work on the instances if the ontology include instances.
Okay, perfect. The name of the plugin, please. Is it Watson Ontology use? This is the name.
So Watson was another one. I have to admit that unfortunately, this is a plugin that was developed only for the Neon toolkit, which was an ontology editor developed by the Neon project. And unfortunately, the Neon toolkit is not maintained anymore. So I'm afraid the plugin doesn't exist anymore. I should probably redevelop it.
Yeah, I think so. Thank you very much.
So other questions? Someone has another question? Don't hesitate. This is the moment. Okay, so if there is no more questions, I think we can thanks again Mathieu for his talk. And
thank you very much.
Okay, and we can say that the first e-colloquium is finished now. Okay, have a nice day, everyone.
Thanks a lot. Bye.